Personally, I'm a little more academic than you might find in some of the private sector industries that are involved in meteorology or hydrology or some of those kinds of things. But just a little background about my company, Baron Weather. Originally was founded in the late 1980s in Huntsville, Alabama. It's called Baron Weather because Bob Baron is a famous, at least in the north part of the state, is a famous broadcast meteorologist. And he was awakened one night, late at night, 2 in the morning, by a large tornado that had made a touchdown and rolled through Huntsville and destroyed a large amount of property, killed 6 people, and he had no warning. He had no way of getting information out to the consumers on TV that something was coming. And in this particular situation, the Weather Service had not issued a tornado warning. So nobody knew. And I know that Tuscaloosa is also familiar with large, dangerous, destructive tornadoes as well. So our company got started and founded to provide improved information to protect lives, save lives, and to reduce property loss when possible. And we were one of the first, we were actually the first commercial broadcast weather company to use what we call storm skits. A skit is basically very familiar to you now, but what direction is your storm going to be traveling? You know, and you can probably get it on your cell phones now. Basically, they're little polygons that they widen out, you know, and so on and so forth. You've got some warning for some cell, the severe thunderstorm warning or a tornado warning, and you see rotation, and somebody on TV or, you know, is saying, "Oh, we see rotation." Well, we developed the technology that allows for the information that's coming out of these dual polarimetric radars to be able to detect, not only to detect the rotation, but also to feed it out to over 170 to 200 television stations in real time before the Weather Service can get the information out. So it's very often the case that the broadcaster will say, well, we're really watching this storm. And in most cases, even the major networks will switch to Baron equipment when there is severe tornadic type weather. So it's almost certain that you've seen graphics in real time depicting the evolution of tornadic thunderstorms and their forecast in the communities and that's what those skits do, is they take the average mean motion of that supercell and they say, okay, we've got this, we know we have a radar couplet, you know, because when you have dual polarimetric radar, you've got polarized radio frequency beams. And one goes polarized this way, one's polarized this way, and so you can get a cross-sectional image when you reprocess that data. And the cross-sections allow you also to detect, is the storm moving away from the radar and its beam, or is it moving toward the radar and its beam? And in general, you'll see kind of one motion or the other motion depending on as it goes around. But in the case of a tornadic thunderstorm, you'll see a very tight couplet where some of that, because it's spinning, some of those now they're projectiles, but those condensed, it could be hail, could be rain, could be even snow, because if it's high enough anyway. But it's detecting all that stuff. Some of it's moving toward the radar, and some of it's moving away as you think of a tornadic cell. And so when you see that tight couplet, that's what allows the radar to detect the potential for a tornado. Now, we don't know from the radar whether that tornado is actually on the ground or not, because the radar beams are kind of going up, they're angled up. And this is not my talk, but it's a little bit about my company. And I could probably talk all day and keep you here till, but I won't do that, I promise. We developed those storm skits. And then broadcast television stations wanted more. And they wanted information more quickly than we could get it from the National Weather Service radars. So we started building C-band radars, which are smaller, and television stations started to buy them. And so in the 90s, we developed a market to deploy radars, weather radars, on that broadcast television at that time, which was a very large market. It's much smaller now because of all of the social media stuff. But at that time, I think and by up to now, and we're still doing that though, it's not quite as big as it was, but I think we have about 120 customized for TV C-band radars that are actually owned by those television stations. Some of them now are dual pole. Originally they were single pole. And then we were selected by NOAA as the company to upgrade the entire NOAA network of National Weather Service radars, 171 of them, from single to dual pole. So we did all the design work that went into all of that, and then we had, up in Huntsville, we had some rented, I think, I don't know, big spaces where you could fit the S-band radars in there, and they'd bring them in, and they'd change out the signal processing and all of that stuff. And then so I think that project took about 3 years or so. In the meantime, they decided they wanted to invest in modeling, and that's where my group came in. In the late 1990s, they were also starting to get involved in some international projects, and the first one that they did before I was hired was a project in the country of Romania, where they actually did a couple of radar upgrades. They upgraded the data center at the National Met Service in Bucharest, and they installed an MM5 model. Now that goes way back. And does anybody know what the WRF model is? Okay, a couple people. WRF, Weather Research and Forecast Model. It was developed in NCAR. Prior to that, there was an earlier generation of that modeling system called the Mesoscale Meteorology Model. And version 5 was the last version. And then the next stage of that project was hydrological modeling. And I had the 10 years prior to that, I was telling Dr. Cohen earlier that the first part of my career was at Supercomputing Center, a nonprofit located in Research Triangle Park, North Carolina. And I was interested in making operational forecasts using those supercomputers. And we had really, really skilled people there that knew how to write the software to make that happen. And we had a partnership with a local television station, and we had our first kind of toes touching into the water of putting specialized broadcast meteorological forecast modeling on TV. That's when Baron came into the picture and said, we think we like you guys. Do you have any experience in hydrology? And the fact was I had, because of another project that I was working on together with a scientist from, at that time, Georgia Tech, who eventually ended up moving to NASA Goddard Space Flight Center. And I still have colleagues and partners there at GSFC, as well as at NCAR. And those were both instrumental in helping us develop this model. Now this model, this hydrological model I'm going to talk about, is one of four. One of four that we deployed operationally for the National Institute for Hydrology and Water Management in Bucharest. And that was certified about 10 years ago for operations. And what it did, and you guys have all heard of the National Water Model, right? Okay. This was it is still functioning as a national water model for Romania. Now, Romania is not nearly as big. Not nearly as big. So, you know, Virginia, North Carolina, and a little part of South Carolina, that's the whole country of Romania. But we also did it on a much smaller rack of blades. You know, I think the largest blade we had in there was maybe a 4-core blade. And so the way we designed the system was that, and fortunately for the country of Romania, I don't have any maps here. I could pull one up if we have extra time, but Carpathian Mountains go through the middle, and then all of the hydrological basins flow off of those mountains, and they all flow either out into the Black Sea or into the Danube River, which curves around most of the country like this. So it was very convenient for us to slice out different major basins and run each basin on one of those blades. And that's what this model does, the model I'm going to show you. Now, at that time, I was working directly with one of the principal developers of the National Water Model, a guy named Dave Gotchis and his partner David Yates at NCAR, as well as my partners at Goddard. As a Baron guy, we were working with those institutions in a tech transfer arrangement. They helped us with some of the hydrology we didn't understand, especially things like channel flow, the importance of channel shapes, and overland flow hydraulics. So they kind of exposed me to some things in hydrology that I didn't know at that point in time. But having been trained in atmospheric dynamics, it wasn't terribly hard to kind of pick it up. But I had to pick up a lot of that as we built the model. And we got to the second generation. We had to build one generation, and it kind of failed. And then we built the second generation, and it was really ready to go. But what it didn't have in it was any way to predict flood inundation. So it was basically, okay, you have rainfall runoff, and somehow you're getting the rain from something. You'd like to be able to get it from radars, if you could, because it's going to be more accurate than a numerical weather prediction model. So we developed a radar, what we call a land data assimilation system, where we would estimate radar rainfall rates and then use those to precondition the soil. So our soil moisture would the pattern of the soil moisture would be reasonably close to what the radar was seeing. But anyway, so in that first version of the model, we had no way to predict flooding. We could predict discharge. I mean, we could predict that, on a hydrograph, the hydrograph would exceed some level, some threat level or some warning level that the agency had determined was going to be of a threat. But we had no way to show them or to predict how far outside of its bank that water would go. And having been involved in writing the code for the solver, I came up with an idea that still seems to have some merit, and that is to couple the two processes together in the model itself. So if the model is aware of, at the same time, where that channel cell is in relationship to where the land surface is, and it knows the depth of the water in the channel, which it does, then when that depth exceeds bankful, then the code I wrote can actually spill that water back out onto the land surface. And then that water is taken through a land surface process, is fed back in, and then you have this rapid exchange. I mean, it's a rapid, in computational time step framework for a 100-meter grid, you're basically exchanging information, flooding information from the land surface into the channel and then back out of the channel every 6 computational time steps. 6 seconds. I mean, sorry, one computational time step at 6 seconds. So every 6 seconds, you're getting, an update, basically, inside the model. You wouldn't see that because the data is only output every hour or something like that. But internally, it has to be handled very rapidly because for mass conservation purposes. So that's the introduction to the talk and Baron and so forth. And so this is going to look a lot like, I don't know where I am here. Am I on screen? and slideshow. All right. So pretend you're at an AGU meeting, because I gave this talk at AGU about a little more than a year ago, at the fall meeting in Chicago. So once I put this feedback in the model, I decided, first of all, we needed to get some information. Well, first of all, I got a patent on it for methods and methods for modeling floods. And so I have a United States patent on this thing. Did that do anything? Probably not. It's interesting, factoid. But I wanted to see how it would work when the rainfall was extremely heavy, because I didn't know if the internal solvers would be stable. I didn't know if it could maintain a flood inundation event when in nature it had been a very long-lived one. And we had one in North Carolina, in my backyard, because my office is in Raleigh on NC State's campus, as opposed to Huntsville, where the big company is. But we had one with Hurricane Florence. And Hurricane Florence dropped between 30 and 35 inches of rain over a large section of southeast and eastern North Carolina in 2018. So I wanted to stress test the model to see, well, can it handle that much rain, and how will it do? Can it actually make the inundation last more than 2 weeks, which is what happened in nature? You know, we had people who had flooded homes well up to their rooftops, and it only gradually receded. So that so the event occurred on the 16th of September, but well into early October, those homes were still flooded. Flooded to the extent that people could not get back in them. Tremendous amount of damage. So I wanted to see, okay, can the model do this? And I guess I was forward-thinking enough to provide the model with what we call an environment variable that just says, you want to turn the inundation on? Turn it on. You want to turn it off? Leave it off. And so we can compare those directly, how the model runs with inundation versus how it runs if it just confines the whole flow to the channel. So we wanted to see how that worked. So I told you a little bit about the background. This was back when we were developing it for Romania. And that's the Matrața et al. 2013 operational validation. We have 2 large, thick reports on calibration of the model that we did in Romania. And then the LN2 flood is what I'm going to talk about today. The first thing that we do in our model, that I think there are other models that do this too. I'm not personally familiar with them, but some of you in here may be. But what we do is we take the DEM, a hydrologically conditioned DEM, and then we further burn that in, so we make, essentially it's in the software itself. The software becomes aware that this grid cell contains a channel, and here are the banks, and it's that deep within that grid cell. So we know that, you know, it has, it's a depth of, say, 3 meters or something like that. Now, how we compute that is another story. But we use these power law relations to estimate a very smoothly changing channel geometry. So typically, channel geometries only change on a sub-basin basis by what's known as Strehler order. But this allows us to very, very smoothly adjust as you go downstream by however, let's say we have a 100-meter grid cell or a 10-meter grid cell, you get a very gradual expansion so that as you go down, the stream can actually hold more water as you go down at a very, very finely discrete geometric basis. Very fine discretization of the geometry of that. And then what we do is we calibrate the power law by using 2 things. Mean annual discharge, if we have the information, and then aerially observed bankful width. So at that time, we would use Google Maps. Here's our outflow. Here's the outflow for the model. Let's see how wide the stream is there, or wide the river is there. There's pretty wide rivers in Romania. How wide is it? 200 meters or however many? Doesn't matter for the model. The model only knows the center line, but if it's 200 meters, the model knows that it's 200 meters. So we then calibrate that, and then the model itself has internally to the model, it spins itself up so that it automatically gives you the mean annual discharge. And so you can kind of iteratively do that. And if you want to, you could iteratively do it to get it really, really, really close. And again, the bankful is explicitly modeled with respect to the DEM. I have a bunch of training that I did. I'm not going to go into that because we don't have time. But what those things do is they permit faithful to the DEM this tight two-way coupling between the runoff-generated ponded water. And basically what's happening is that the river is flooding and it's making a lake. A small one, but you've heard about the lake that was just made in Death Valley? You guys heard about that? It's been in the news recently. They had so much rain in Death Valley about a month ago that it created lakes where they had never have been before. In dry lake beds that have probably been dry for hundreds of years. And if you look up online, you can see the pictures of those lakes in Death Valley. An inundation does kind of the same thing. It creates a lake. The question is, how long does that lake live? What are its actual evolution? How far does it go? And who does it impact? So our company is really interested in impact forecasting. We want to make, because of value, the value chain says that if I can more finely and more faithfully forecast impacts, and inundation is very hard to forecast, then we can do a better job of preparing local emergency management, families, businesses, folks. Well, the water's not going to come to your level, but it is going to come here. That's the whole idea. And then this is all done within the model, so we don't have to post-process anything. So with the National Water Model, it's different. I think I have a chart here. And I won't go into this. Dr. Cohen is going to have a copy of this, and I'd be happy to share it with anyone who wants a copy, and you can go through it and look at it yourselves. But here's a comparison of the different processes that are used in WRF-Hydro, the National Water Model, and our LN2 flood. And in this optional two-way coupling is not something that's available in either of those models. And in the National Water Model, the flows are abstracted into a completely separate layer of software that manages the stream flow. So we don't have streams embedded in the DEM in the National Water Model. The National Water Model simply provides runoff, and then there's a separate stream layer, unless that's changed, Dr. Cohen. I don't think it's changed, right? So there's no way to get water out of the streams back onto the land surface in the National Water Model. Our model does have that. Thus, there seems to be some interest from NOAA and Cairo. So here's this is the stress test case. Historic flooding, North Carolina, the Cape Fear River Basin, which if you know the map of North Carolina, along the coastline, Wilmington is the exit point for the Cape Fear River. And then it has several branches. There's a north branch, which goes up toward Chinkapin, a little town called Chinkapin, which is in the southeast part of the state. You'll see it on the map. And there's a USGS gauge there, so it's a good place to set your model up and calibrate it. We also knew that Chinkapin had been very, very badly flooded. So we knew that floodwaters were well up to rooftops. So let's try it. And so here's an overview of the village of Chinkapin unflooded, and that little inset shows you what it looked like when it was flooded. And then the Cape Fear River is down here. It just kind of comes down in here, and then there's a gauge right down in here. So one can see that this volunteer fire and rescue squad was, kind of almost completely underwater and everything. And then if you look at the USGS estimates of discharge, the gauge washed away. So pretty much it took them until the 27th of September to put a gauge back in. And this was all estimated, in terms of estimating the recession curve. And then this is gauge height, but we don't know how high the water got. And I'm assuming that at about 25 feet is when the inundation started, or at least the gauge, washed away at that point in time. Maybe it got up to where it was to the bridge level, and I'm not really sure. Civil engineers would know exactly how they install those gauges, so I'm not that. And so anyway, but this is the data that we had from USGS. And the recession back to flood stage took until about the 25th of September. That's that one right there. I guess that light blue is flood stage. But I think that's an estimate because the aerial photos showed that the flooding lasted a lot longer. This is just a diagram that shows you a little bit about the track of Hurricane Florence. And on the left there is a map of the entire Cape Fear River. And then that north branch that's going up to the right side there, it says, I think it says North Branch Cape Fear. That's what we modeled. And then this is rainfall falling from Hurricane Florence, and 25 to 29 inches, 30 to 34, and the dark greens were 35 to 36. So that's 3 feet of rain. 3 feet of rain. How can a model handle that? How can a hydraulic model? I don't know. I mean, I was concerned that it wouldn't. So I really wanted to stress test it and see what would happen. So we designed it to capture just the basin that was north of Chinkopin. And on that upper right one there is something that Dr. Cohen would be very interested in. There was some commercial company that provided flood inundation estimates from satellite. And I think this was a pretty obvious, probably a pretty obvious event because the flooding was so severe. Probably was fairly easy for them to detect, feet of water on the ground. And so the green areas are typically saturated, and then the blue areas are, the green areas are floodplains, and then the blue areas are flooding beyond floodplains, I think is a way to interpret that. So we ran the model for 6 years to calibrate it. We used a data set that's produced by NASA called National Land Data Assimilation. And what it does is it provides you with many, many, many years, going all the way back to 1995, of radar-derived precipitation. So note, not model, not reanalysis, radar-derived precipitation. And in the initial calibration, we omitted the Florence period. And what we call, one of the measurement indices for hydrological models is called the Nash-Sutcliffe Index. Is anybody familiar with that? So critical success index, similar to that. If it's 0, you don't have any skill. You don't have any skill above average. But something that's above that has a little bit of skill. And the uncalibrated model had a little bit of skill. But when we calibrated it, we got to 0.82, which is a good score for the NSE. And then this was, I did a Levenberg-Marquardt fit of monthly mean discharge. And you can see that the 1-to-1 line and the green line are really, really, really close. And then, of course, that one out there, that outlier out there is Florence. And then calibration results were all done with feedback turned off, because once you have feedback turned on, you lose the water in the channel, and you can't calibrate it against the observations. And of course, the observations are in blue, and those were the same ones that I just showed you from the USGS gauge estimates. And this is all discharge based. So, we had a pretty good shape, but not nearly the magnitude. And it's a log scale on the left. So, we did quite a lot better once we calibrated the model. So now I'm going to show you a series of maps. Pre-storm on the left shows you nothing has inundated at all. So, but with the post-storm, and that one's September 14th. The storm occurred late 14th, 15th, 16th, and part of the 17th. If we don't allow the water to come out of the channel, you basically all you see is a little bit of water that has ponded on the land surface itself because the land surface has gotten saturated. So you have a little bit of runoff that's ponded there. But that's it. You don't have any flooding, coming back. So you can see some reds and greens and stuff as opposed to no floods there. But you can see some much higher discharge values in the channel, but no inundation. Now, when we turn it on, we can see inundation switch off, which is the last map on the last slide that I showed you. But when the inundation switch is turned on September 17th, all of that area is now flooded outside the channel. And it's all flooded back onto the land surface. So you can see the huge difference between inundation turned off and inundation turned on in the model. This is another illustration of what happens to the land surface or the soil column, because it's the antecedent soil column and it's the maintenance of saturation in the soil column that causes the inundation event to last a long time. If that soil column was dry, it would drain at its standard rate. If we got a thunderstorm this afternoon, it wouldn't sit around on the grass very long because it'd all drain in. And when the inundation switch is turned off, this shows you the depth to the shallow water table, which is going to be meters below ground. So you can see some depth to the shallow water table. These are areas where the shallow water table was high because we model the water table in the model. And in some areas where it was basically right down at the very bottom of the soil column, which is 2 meters down. But some areas where right in these ephemeral areas where water is draining down toward the streams, then you get some lake type development. Well, this is in the soil column, pretty close to saturation. And then on the right, of course, is the satellite estimate of where it was inundated. And this is a larger one. But if I go back to this plot, you can see a real similarity between our inundated result and the satellite derived observations. Pretty similar, right? So that gives us confidence. And second of all, the model ran. So it didn't become unstable with that much water, and I'll show you in a bit how much water there was. But when we turn on inundation, you can see that all of the soil column here in these inundated areas is saturated. Now compare that with this. It's pretty darn close. I was kind of stunned by that result. But that is showing you how saturated the soil became as a result of water spilling back from the channel onto the land surface. It just maintained soil saturation for weeks in that floodplain. It created a new floodplain, basically. Now I'm going to show you, I believe this is and I've got some animations here, and these are hourlies. So this is showing you the inundation expressed as the base 10 logarithm of the depth in inches. And the dates and times are down there. So September 21st, 22nd, 23rd, 24th, 25th, 26th, 7th, 8th. I think I ran up to the 30th, maybe. I can't remember. Yeah, okay, so then it started. So I ran a 16-day simulation. And at the end of 16 days, the inundation hadn't gone away in some places. So that's cool. Now, what does it look like when you zoom in on a confluence? So the arrows show the direction of flow in the main stem of the stream channels. But the reds show the extent in grid space of the inundated waters as they flow out of the channels in the model. So we'll just watch that for a bit and then let it repeat. And this is the confluence of the, it's called the Goshen confluence, which is about halfway up into this basin. And it's up at the very top of that little panel on the right is where the Goshen confluence is. There was actually two, I believe there were two major pulses of flood waters that you can see if you look closely in this. I think we're past the second one. But yeah, so logarithm 10, so, 10 squared is 100 inches. So that, if you're up in the dark reds, that's a lot of water. Kind of 1.5, 10 to the 1.5 power. Yeah, that's a lot of water on the surface. And that's in the model. And the model Overland 2D hydraulics is managing all the flows outside the channel. And inside the channel, we use two solvers when we have the inundation turned on. For everything that's above bankful, we let the overland flow handle that part of the downstream flow. And everything that's within bankful, we let the Manning's equation handle the stream flow in the stream flow. So that is a reasonable attempt to account for the fact that once waters get above bankful in a normal situation, there's going to be a lot of debris in the water. It's going to pile up. There's going to be kind of junk in there. So it may not flow quite as fast. So for over bankful flow in the channel, we let the overland flow handle that. And then for in bankful flow up to the bankful, the actual trapezoidal shape and all that, that's handled by those equations. So two sets of equations for water that's in bankful. Now, how did we evaluate this? Well, there was some NOAA overflight data that took place because this was such an outlier event that occurred. And so NOAA emergency response collected, and FEMA did some overflights. And so we selected out the ones that were relevant to us, and that red outline in the left panel there shows you that there was a little tongue of those overflights that came over. So we used that data, and there's a comparison of non-flooded area versus flooded area. And the red lines show the map of, this red area shows the map of where the flights actually flew. So you can see how much darker the land surface is there than here, and you can see a lot of agricultural buildings and all that kind of stuff, and I wouldn't say it's gone, but it's pretty darn covered. So how did we do right close to the town of Chinkapin? So here's another animation, and there's the overflight data, which took place on, oh gosh, I think it was September 18th. And again, the animation on the right is showing you the overall 16-day period of time. So we'll just kind of let that go. So this is darn close. So the outflow point is right here. The gauge is kind of right in here. Chinkapin, this is another little stream here, and then the village of Chinkapin is right in here. So in my guess, we probably underestimated the lateral extent of the inundation in the village of Chinkapin a little bit, but not as badly as the National Weather Service did. So, and I'll show you that in a second. So right down by that village, right in here, there's the overflight of the village. So you can see all of these ephemeral lakes. They're all flooded. And some of these buildings, you can still see them, but a lot of them along Highway 50 are flooded. But normally, you know, this is all ag fields here. And, you know, it's almost certain that it was flooded underneath the trees, too. You just couldn't see it. So what I did here on the right-hand map was I took the maximum inundation across that 16-day period and mapped it here with Highway 50. That's where that fire and rescue squad is. And anything that is in the lightest of the light browns did not get any inundation. So I think most of this got a little bit, and that's how these bin numbers go. So bins 21 to 40 show 5-inch ponded water depth increments. Oh, and I guess unflooded terrain is shown in brown. And so this is essentially the DEM terrain, and then you get inundation in 5-inch increments in the blues up to, I guess, 20 to 40, and then 40 to 50. There's another, I guess it's more. I can't remember exactly. I'll have to, if anybody has a question on that, I can get it. I wrote a paper on this as well, so it is published. But there you can see what the National Weather Service estimated to have been inundated from AHAPS, which is their Advanced Hydrological Prediction System. And that was the maximum inundation that they thought would ever occur for this event. And clearly, you know, they don't have anything in here. Here's the Cape Fear River here, and there's the gauge. This is the maximum that they suggested. All of this was inundated. We saw it. We can see it right here. And there's the fire and rescue squad right there. Now, our model picked up on a lot of this stuff and some of this stuff in here, but not quite as much as actually occurred in nature. So we can go back and look at that. So here's our model. So here's the village of Chinkapin. So we definitely have the inundation in here. And even up through here, the fire and rescue squad is there, and then all of this is inundated. And there's a little bit here, and that might be due to forested or something like that in the DEM and in the land surface. I'm not really sure. I haven't done the investigation as to exactly. Oh, there is an explanation, however. And the explanation is that this is the explanation. The explanation is that the bottom boundary condition in the model was not. The stream was allowed to free flow instead of having further inundation downstream, which really did occur. And if we'd had modeled actually another, I'd say maybe 150 kilometers downstream, this would have been completely inundated. Because we would have had, there's so much water got backed up. It's just water's getting backed up like, you know, you back up a toilet. You know, as far down as you go, you know, if you let it free flow just below, then there's not going to be a whole lot to come out. But, you know, when it's backed up, if the plumber has to come in and, you know, plumb out the whole system to get that was the reason that we didn't pick this up, I'm sure, positive, sure about that. Okay, so concluding slides. We've described a novel implementation among a family of models that's fairly closely related to WRF-Hydro. The LIS-NOAH, so NOAA land surface model, LIS, NASA Land Information System, 2, version 2, and then F for flood, permits the simulation of flood inundation fully online. And for this Hurricane Florence case, the event maximum inundation compares really well with a satellite-based OBS throughout the modeled sub-basin. We didn't have to do anything to the solver at all. It didn't exhibit any instabilities that would cause the model to crash. And it does, as I pointed out, probably due to the outflow boundary condition, it underestimates the extent of the max inundation near Chinkapin, but it outperforms AHAP's 100-year flood estimate. And these are just some technical summary stuff and blah, blah, blah. And then this last slide shows you it's the same graphic, but this is the maximum flood inundation over the whole basin for the whole event. So you can basically see, now if you could forecast that in advance, you would really, really have better information to provide, to the communities that draw their livelihoods from the river. And that concludes my talk. Any questions?